This screencast is to help you review for chemical formulas part of the chemistry curriculum. So what the state says that you need to be sure to know about chemical formulas. First, how to name and write the formulas or the correct formulas for everything. The first little bullet point here says write binary compounds. Now remember, binary just means two things of two nonmetals. So that means it's going to have covalent bonds. If it has covalent bonds, then you're going to need to use those prefixes: mono, di, tri, tetra, penta, hexa. And you have a paper. Now it's for ionic. Let's look at covalent. You're always going to write the less electronegative element first, and that's usually the first one written. And you only have to give a prefix if more than one of that atom is present. Then you write the second element. You add an appropriate prefix depending on the number of atoms present, and then you add the root of the second element's name, and then they end in IDE. And there's a list of your prefixes in case you forgot. So let's look at one of these. The example I'd like to start off with is CO2. So you're going to name the first element, and it doesn't need a prefix because we have only one of those. We have two oxygens, so for the second element it always gets a prefix. So that would be di for 2, ox for the root of the second element's name, and then IDE at the end. So you need to pay attention to what you have before you decide how to name it. CO would be carbon, and then second element always gets a prefix, so that would be mon, and then root of the second element's name, ox, and then they all end in IDE, carbon monoxide. You could have something like this, okay, and that would be diphosphorus trichloride. In this case, the first element, there was more than one of those, so it does get a prefix, but otherwise you do not change that first element's name at all. Second element, prefix, root, and then IDE at the end. Going the other way, if you are given names, when you see a name that has prefixes in it, like in this case, diphosphorus trichloride, when you see these prefixes in here, that is a clue that this is a molecule. And you're going to write the formula, you're going to write exactly what it says. So diphosphorus, that means I have 2 of those, and then trichloride, that means I have 3 chlorines. There are no charges to crisscross or anything else with covalent bonds, and that involves 2 nonmetals. Now, second one is write binary compounds of a metal and a nonmetal. So these are our ionic bonds, and with those we do have to deal with charges. So look at the formula. If you see a metal or one of our positive polyatomic ions, you are going to have to be using the ionic, the charges, and you are going to have to crisscross for those. So let's look at the instructions for that and the crisscross method. Remember that the resulting formula for a compound must have a total charge of 0. Positive ion always goes first, and then the negative ion. You're going to cross the oxidation numbers, or those charges. If they are both the same, don't cross them. They end up canceling each other out. Don't cross ones, and don't cross signs. If a polyatomic ion needs a subscript, you must use parentheses. Be careful with hydroxide. Don't let it get you. And if the final answer has subscripts that can be reduced, they must be reduced. Now this is for ionic only. Because we're operating off of those formula units, they must be reduced. And often on the final exam, they will use formulas that need to be reduced for ionic, even though that's not exactly fair. So let's look at these. So for example, if I have something like magnesium and iodine that are going to bond. Magnesium is my metal. It is in group 2 on the periodic table, so it likes to have a charge of 2 positive. Iodine is I. It is a halogen, so it has 7 valence electrons. That means it only needs 1 more, so it likes to have a charge of negative. The sum of the oxidation numbers is not 0, so you got to crisscross. And we don't cross signs and we don't cross ones, so it's just MgI2. Another case would be maybe calcium, and I'm going to add a polyatomic ion in here. Carbonate. Remember that you do have a list of all your polyatomic ions on your reference tables. Here, the sum of the oxidation numbers is the same. Calcium wants to give up 2 electrons, carbonate needs 2 electrons, so they're going to end up canceling each other out, and you're just going to get calcium carbonate. Now, going the other way when you are naming these. When you are naming these, remember that there are no dies or tries. You write the name of the first element, you write the root of the second element or ion. If it ends in an element, the ending must be changed to IDE. If the compound ends in a polyatomic ion, do not change the ending, just write that polyatomic ion down. So let's look at that with my 2 examples. Here I see it's a metal and a nonmetal, so no dies or tries, and this is just going to be magnesium, iode, and then IDE at the end because it ends in an element. This one will end up being calcium, and then it ends in a polyatomic ion, so I'm just going to write the name of the polyatomic ion, carbonate. And that's it. That's how you name ionic compounds. But I will tell you, probably an answer choice for this one would be magnesium diiodide, and that is incorrect for something that has ionic bonds. Now we're going to talk about how to name acids. Now we've had a lot of exposure with this, but you need to make sure that you know how to do this, and really it's the difference between whether you have hydrogen bonded to an element or hydrogen bonded to a polyatomic ion. So with acids, if it's hydrogen bonded to another element, it has a hydro prefix. Then you're going to add the root of the second element's name, and then "ic" to the end, and then you write the word acid. If it is an acid with a polyatomic ion, there is no hydro, and that's really the distinguishing factor between these. You write down the polyatomic ion used, and you're going to change the ending. "ate" changes to "ic", and "ite" changes to "us", and then you're going to write acid at the end. So, if we look at an example of that, if I have HCl, this is hydrogen in an element, so it is hydro, and then the root of the second element's name, chlor, ic, and acid. We know it's an acid because it has that hydrogen there at the beginning. If we have hydrogen and a polyatomic ion, there is no hydro. The polyatomic ion that we see here is nitrate. We change the ending of the polyatomic ion. "ate" changes to "ic", and then you write the word acid in there. So this is nitric acid. Going the other way on these, if you see the word hydro in there, you know it's hydrogen and an element. So this would be hydrogen, and it always likes to have one positive charge. And then it's going to be bonded to chlorine, which is a halogen, which likes one negative. The sum of the oxidation numbers is 0, so they cancel out. So the formula is just HCl. So when you write the formulas, it's going to be a lot like ionic. Nitric acid, it's a hydrogen because that's what all acids start with. And then "ic" came from 8, so this is nitrate. The sum of the oxidation numbers is 0, so they cancel out, but they don't always. Now I'm going to go over what a hydrate is. Remember, a hydrate is an ionic compound that has water molecules trapped inside, and that does affect the mass of a particular compound, so it's important to know. These formulas look like this. So here we have calcium sulfate, that's our ionic compound that's there. There is a dot, and then the number of water molecules that are trapped in each formula unit of that particular ionic substance. So this one would be calcium sulfate dihydrate. You're going to use the same prefix here that you use with covalent bonding molecules. Alright, then with writing the formulas for hydrates, you write the chemical formula, the dot, the number of water molecules, and then H2O. Okay, next thing on the list is describe macromolecules and network solids. So they have a list of ones here, and we're going to look at the structure of those. But they want you to know that these are a class of molecules with unique properties. It's the way the atoms are linked together, whether it's by bonds or by intermolecular forces. So here we have the hydrogen bond, that really strong intermolecular force, not as strong as a bond. Even though it's called hydrogen bonding, it's not as strong as a bond, but it is still a strong force of attraction. And so when a lot of water molecules get together, they form these networks. So this would be formed in ice, probably the easiest, but also in liquid water, although those molecules would have a little more energy to move around. But these hydrogen bonds would have to be broken before you mix it with anything else. Then here we have a structure of a diamond and graphite. Remember, both of these things are made of carbon and carbon only. What makes a difference is in the way they are linked together. In a diamond, the carbon atoms are covalently bonded to other carbon atoms in this three-dimensional network. Network covalent bonds ends up being stronger than overall than ionic bonds, even though ionic bonds are stronger than covalent. When they occur in networks, covalent actually is stronger than ionic. In graphite, and this is your pencil lead, the carbons are not bonded in 3 dimensions, only in 2 dimensions, into sheets, and these sheets are linked together just by intermolecular forces of attraction, which makes it handy to write with. A diamond, not so much. All right, now talking about polymers. Polymers, that means many parts, and they're made up of, the parts they're made up of are called monomers. So that's the one part, and it's just replicated over and over. So this is a vinyl monomer, and then when we link this up together, we get polyvinyl chloride. And this can be used like PVC in pipes and things like that. So we can do a lot of things with polymers by putting lots of different monomers together, and they're going to have their own properties depending on what atoms are involved here. This that I have right here is the structure for nylon. We have this structure that is repeated. That's why it has this little N here many, many, many times, depending on what type of nylon we're making. And that can be used in shoes, bathing suits, athletic shorts. I've even seen it in fingernail polish. So lots of uses for polymers. Again, this would be the monomer for that one, and it's just repeated many times. Let's look at proteins in hair. This is actually the structure for curly hair. And here you can see the ball and stick models with those intermolecular forces. Here we actually have the elements that are involved here. And these R's would be more C's and H's that they're linked to. And you can see that there are some hydrogen bonding going on here in this curly hair. Probably that is what adds up to it staying in that curly shape. Then we have DNA. You studied this a lot in biology, but there's a lot of chemistry in there. Phosphate groups are the backbone to DNA, that PO4 negative. You can see that here, here, and here, and they provide that backbone that your A, T, G, C are attached to. Then the links that are going through here are going to end up being, you can see it over here, they're hydrogen bonds. And you can see the hydrogen directly bonded to the nitrogen, and it's attracted to the unshared pair that is on this nitrogen. So hydrogen bonds hold together your DNA. Now let's talk about how to calculate empirical formula from mass or percent using experimental data. So an empirical formula is the lowest whole number ratio of atoms, and we use it because from that we can figure out what a particular molecule is, because we can go from an empirical formula to a molecular formula. But first let's just focus on an empirical formula. Remember, it is the lowest whole number ratio of the atoms, so if you're asked to pick out an empirical formula, you're going to look for the one that has the lowest ratio of atoms and reduce it down to the lowest possible numbers that you can. Alright, when we are looking for empirical formula, the way we do that is we had a little rhyme to remember. Percent to mass, mass to mole, divide by small, multiply till whole. And we have a little problem here where we're going to try and figure out the empirical formula of something with these percentages, so percent compositions. So the first thing to do is we take our percent and we're going to change it to mass. And if we assume 100 grams, that makes this calculation very, very easy. So we have 32.38 grams of sodium in a 100 gram sample. We would have 22.65 grams of sulfur, and we would have 44.99 grams of oxygen. So if they give you percentages, go ahead and assume 100 grams and drop the percent and put grams. Sometimes they will just give you grams. If that's the case, just don't do this part of the rhyme and just do mass to mole. Now we're going to convert each of these to moles. So we have 22.99 grams and 1 mole of sodium. We have 32.07 grams and 1 mole of sulfur. And we have 16 grams and 1 mole of oxygen. Then we'll need to get our moles for each of these. You want to maintain the same number of sig figs, so I get 1.408. Then I get 0.7063, and again these are all moles. And then I have 2.812 moles of oxygen. Then we're going to divide by the smallest number. This is the smallest number here, and so I'm going to divide all of those by that number. In this case, it comes out, this one's going to be 1. This one, when I divide those two, I get 1.993, which is close enough to 2 to call it 2. Remember, it has to be within 0.1. Alright, so if I got 2.5 here, then I would have to do this multiply to a whole at the end. And then when I divide these two, I end up with 3.981. So again, that's close enough to 4 to call that 4. Again, if it were 3.5, then I would have to multiply everything by 2. But that's not the case. We don't have to multiply to a whole on this one. Alright, this tells us that we have 2 sodiums, so it's going to be Na2, 1 sulfur, and 4 oxygens. And this is sodium sulfate. That's how you do an empirical formula. Now, if you were going to try and figure out how to do a molecular formula, the way you find a molecular formula, it's going to be some multiple of this. Again, this isn't a molecule, so it's not going to have a molecular formula. But to find the molecular formula, you're going to find that little X factor, what we have to multiply all the subscripts by. And that is your molecular formula mass, and that's always given to you in the problem, and divided by your empirical formula mass. And that's just the molar mass of your empirical formula. So if we had a situation where we had an empirical formula of, just move this up just a little bit. If we had an empirical formula of P2O5, and we found that the molecular formula mass was, and they tell us that in the problem, was 283.89 grams per mole. I'm going to find my little X factor, so that's going to be 283.89 divided by the molar mass of this guy. And when I add all of that up, I get 141.94. And so I get an X factor of 2. And that should come out to a whole number every single time. If it doesn't, you've done something wrong and probably just have these two flipped. It's always big number divided by small number in this case. So with this 2, what I need to do is I need to multiply both the subscripts by 2. And so I get P4O10. And that's how you do a molecular formula. Next we have determine the percent composition by mass for a given compound. So working with these, the way you're going to find the percent composition is it's always part divided by whole times 100, and that'll give us our percent composition for each one. So if we're trying to find the percent composition of copper 1 sulfide, Then what we would need to do first is we would need to get the molar mass of everything involved here. So I've got 2 coppers and I have 1 sulfur. Each copper is going to have a molar mass of 63.55 and each sulfur has a molar mass of 32.07. When I add those together, I get a total molar mass of 159.2 grams per mole. Then what I'm going to do is to find, let's say, the percent sulfur in this compound. I put the mass of all the sulfurs, and I just have 1, so that's going to be that 32.07, and then over the mass of the whole thing, 2, and then times 100, and I would end up in this case with 20.14% sulfur in this compound. That means we have about 80% there in for copper. So I could just subtract this from 100, or I could do the same fashion with copper. I would just need to make sure that on top I put the mass of all the coppers present. We could also do this with a hydrate. So if I had something like sodium carbonate, decahydrate, then, and I wanted to know the percent composition of, or percent water in this compound, the first thing I'm going to do is find the molar mass of this guy, and I get a molar mass of this, let's see, of right around 100. Just estimate, and this mass is 180. Let's say it's 106, and this is 180. Then what we would do is to get the mass of the whole thing, and this is 10 times the molar mass of water, which is 18.02. So what we're going to do is add those together to get the mass of the whole thing. So you get a mass of the whole thing, and here I have more exact numbers. 0.14. That's the mass of that hydrate. To find the percent water, what we're going to do is the mass of all the waters, and that's 108.2 grams per mole, over the molar mass of the whole thing, including the waters. And then times 100, and you would end up with this compound at 62.98% water. So over half of it is of its mass is water, and again that does play a role when we are trying to purchase things based on weight.